Hello again. Hopefully this is concluding the field from a current bit. I'm going to try to get both of these in the same case. These are both the sort of problem that you would get from Ampere's law. We talked about a long wire and what the field is around it. We can ask, what if I have... So current goes in, it follows around this loop, and then it comes out the wire there. And so we can ask, what does the field look like around this loop? And so if I right hand rule this, do the grab your right hand rule, my fingers are always going to go through into the board through the center of the loop. So that's my field going through the center of the loop. Now, if I want to know the field at the edge of the loop, near the wire, that's a painful integral. And I think it's beyond what y'all should be expected to do. This is a sort of thing where I didn't see this until grad school, so... If you want to know what it is at the center, that's not quite as bad. You can take and say, well, any tiny little point here of this loop is going to look like a bit of wire a distance r away. So this we know is mu naught I over 2 pi r is b. And we're going to add up over this whole thing. Of course, we do have a problem is half the field is inside the loop, half the field is outside of the loop. And so that's going to explain why we're eventually dividing by 2 again. But the gist is, at the center of a loop, the field looks like mu naught I over 2r. Not 2 pi r, 2r. And that's because we're taking individual little segments, which look like mu naught I over 2 pi r. We're adding them all up, and we get 2 pi of those. And so that cancels. And then that's supposed to be the total field, but half of it's outside, half of it's inside, so you get a 2. That's a very hand-wavy explanation. So I just want you to find it plausible that this is the answer. If you don't find it plausible, then by all means, sit down with Ampere's law and try to understand it. That's less... There's a few places that this comes up. If you're a person of my age, you would have seen antennas which fit on the back of your television, which look like these single loops. And possibly you might have seen that in some context. Most of the time, it's the other thing over here, the solenoids, which is the thing you experience. And what we're going to do is say, well, what happens if I go twice around this loop? Well, then I'd put in a 2 here. And if I go a third time around, I'd put in a 3. So we can put in if there's in terms. But eventually, you get something that doesn't look like a loop anymore. You get something that looks a lot different. So I'm going to draw this edge on. Like that. So I drew a few turns, but imagine that there's a lot more turns here. Now, outside of this is hard to do, and near these edges, but if we can get right in the center, we can ask what the field is. And if we pass the current through it, and then we look at this and say, well, the wire is going in front around the coil the way it appears. where the goal is to get that the field through this is this way, it ends up being uniform. And it ends up being a matter of the density of these coils. But it doesn't depend on the radius anymore. It'll end up being mu naught, a lowercase n times the current. And lowercase n is n over L, where this is L and there's n turns. And this is a solenoid. And that gets used a lot more in your in your daily life. Is if you have a doorbell on your house, a solenoid is going to make the bell. I'm talking an actual bell, not one of these electrical ones. If you have a car, you have solenoids in your car that do things. You know, they act as relays. You're going to have various things where you pass an electric current, it's going to activate some mechanical thing, a solenoid. So there's several of these. They come up in a few different places. That's kind of the three things I wanted you to know. I'm checking to make sure that we're still recording. The currents, so this is a review. For wire, B is mu naught I over 2 pi r. For a loop, B is mu naught I, maybe times n over 2r. And then for a solenoid, it's this. So with that, that's the cases where we're going to make magnetic fields from currents. There's other ways to do it. We can come up with some weird geometries. Your textbook, I know, shows you something that looks like this. And it asks you what the magnetic field at that dot is. And this doesn't, these two aren't going to create magnetic field there because the current's headed in that direction. This bit you integrate over. And so if this is 90 degrees, well, you take the loop thing and you divide by 4. Literally, that's about what it's going to end up being. But they show you the integral that you have to go through. So if that's your interest, if you want to be a physicist, I would recommend looking at those examples thoroughly. But if you're going to be doctor or artist or politician, then maybe you should just hit up the highlights, and that's what I try to do in the handout instructions. So when you got your stuff emailed, I sent the email out to you, and you got this packet in the mail. I said, glance over some of these things, and I pointed out which things were important, and this is it. So with that, I reckon things should be okay. So I'm going to upload these. I'm going to try to make some calculation videos later, and I want to pick some problems so that we can calculate through them. You saw one as we did, but they're, you kind of have to prepare for them. So if you have questions, please email me. All right.